All right, so now we're going to be taking a look at the laws of thermodynamics. And this is going to give us an sort of a view of physical science, chemistry, physics, for example, from the perspective of energy changes. So the word thermodynamics itself literally means heat and power. When we talk about the study of thermodynamics, what we are looking at is the study of energy changes and their relationships. And in most cases, not all cases, but in most cases, that energy is going to be in the form of heat. So thermal energy, in other words, is what we're going to be looking at and focusing on most frequently. So thermal energy is the type of energy that we'll encounter or that we're maybe used to more frequently than other forms of energy. But as we know, there are many other forms of energy that we do encounter. So there are a couple laws that we need to talk about when it comes to thermodynamics, and at least one of them you have heard about or we've talked about before. So the first law of thermodynamics is simply the law of conservation of energy. Now, we saw this law before when we talked about the law of conservation of matter or the law of conservation of mass. When we balance chemical equations, for example, the whole point of balancing those was so that we didn't create something out of nothing or we didn't lose stuff along the way. Well, another way of stating that, another sort of interpretation of that is a law of conservation of energy, which says that energy is neither created nor destroyed. But can be interconverted or can be converted from one form to other forms. And in some cases, those other forms are useful. So forms or form. In some cases, they're not so useful. All right, so energy is neither created nor destroyed in any process, whether that process is a brick falling or a candle burning or an ice cube melting. In those processes, energy is simply converted from one form to another. So for example, if you think about candle burning, okay, so there's our candle, and there's our flame. And so what's happening in this process, right? Well, you have the potential energy in the candle wax itself. So there's chemical potential energy, which is the energy that can be converted into more useful energy. And that's usually what you have in, in fuels, whether it's food or in this case, a wax of the candle, gasoline, all of that would be chemical potential energy. Now, when we light the candle, right, we obviously have that chemical potential energy is now converted into other forms of energy. So, for example, we obviously see the flame, that's light energy. Then we also get, if you put your hand close to it, you'll see that there's heat or thermal energy being generated as well. Okay, and some of those forms are more useful than others. So for instance, you light a candle, most likely, so that you can see. So we're taking advantage of the light energy, right? Heat energy is also produced. We probably don't use a candle to heat our homes, but that's a byproduct of that. And it may not be as useful a form of energy as the light energy that's produced. So we do have this interconversion, chemical potential energy in this case that we're starting off with in the wax, being converted to these other forms of energy. Some are useful, some are not so useful, right? So that's the first law of thermodynamics, which is just simply the law of conservation of energy. We can define the first law of thermodynamics, law of conservation energy, in a couple of different ways that would make a little bit more sense. Another way of stating the fact that energy is neither created nor destroyed, we can say that the energy of the universe is constant, meaning it doesn't change. Now, when we use the term universe here in chemistry or physics, really what we're defining are two different things. So the universe is made up of whatever it is that we're studying or that we're looking into, which is the system. So whatever is being studied. And then the universe is also composed of the surroundings. Okay, and the surroundings are just everything other than the system. So we'll say everything else. So in other words, in terms of a scientific setting, we're talking about universe in a general sense, kind of get overwhelmed a little bit. But here we're defining two components. So the universe is simply the sum of the system plus the surroundings. So according then to this first law of thermodynamics, whatever energy is lost, so E for energy, is lost, put that in quotations, by the system, the thing that we're studying, guess where it goes? It's going to be gained by the surroundings, everything else that's around it. So what we can say then is the change in energy of the universe. So we know how to represent the change in something. The change in, we use the delta sign, energy E, and then universe, we'll put this as a subscript, right, is according to the first law of thermodynamics is actually zero, right? Because whatever is lost by the system has to be gained by the surroundings. Similarly, whatever is gained by the system has to be lost by the surroundings, right? So in other words, we can state this then that the change in energy of the system has to be equal to the opposite of the change in energy of the surroundings. And again, that energy could be all different forms: heat energy, thermal energy, light energy, whatever. So if you think about, let's say, an example that you did in the lab or that you will be doing in the lab, we have a test tube and we have our solution in here. We have, start off with one thing, we add another thing to it. Let's say then that we perform this reaction. Okay, so the reaction occurs, Rx in is reaction, occurs in the test tube. Okay, and let's say that this reaction is an exothermic reaction. So in this case, the reaction is whatever's happening in here, that is our system, right? So whatever's in the test tube, okay, that is the system that we're studying. System is the reaction. Now, the surroundings then would be everything else, right? So the surroundings would be the test tube, okay? Maybe the test tube rack that the test tube is sitting in, maybe the bench top that the rack is sitting on, maybe the room that the bench top is in, maybe the building that the room is in, maybe the city that the building, and etc., etc. So everything else other than the system is what the surroundings is. So for an exothermic reaction, right, obviously here our system is going to lose, gives off energy, okay, for exothermic. Okay, and where is that energy going to go? Let's assume that this is heat energy that we're talking about because of exothermic reaction. Okay, so it's losing that heat energy. Well, the heat energy then is going to be gained by the surroundings. Okay, and we just said that the surroundings is everything else other than the reaction. So in other words, if you are holding this test tube, guess what? The test tube is going to absorb that heat, gain that heat, and the test tube will feel warm, right? And that's one of the things that we talked about in lab, looking for evidence of chemical reactions. If it's an exothermic reaction, test tube feels warmer. This is a direct application of this first law of thermodynamics, right? And the opposite would be true as well. If the system absorbs heat, right, where is that heat going to come from? It's going to come from the surroundings. So the surroundings then is losing heat. So the test tube will actually feel cooler for an endothermic reaction. All right, so the next thing that we need to introduce and explain a little bit when it comes to thermodynamics is this idea of spontaneous versus non-spontaneous processes. And we'll first of all take a look at what spontaneous is. And the name kind of suggests where we're going with this. But a spontaneous process is one that proceeds on its own without any outside assistance. Okay. So for example, all right, if you, and it's a very simple case, if you're in a room, imagine that this is a room, and you enter through the door over here, and you have a cologne bottle, like this, and then you spray some cologne into the room, just one big puff of the cologne. What is going to happen spontaneously? Well, in this case, this is our cologne or perfume, if you will. Okay, these perfume molecules will spontaneously spread out. Right, so eventually, if you were standing over in this corner of the room, right, when you first spray the perfume, you don't smell it. But over the course of time, maybe and after 30 minutes or so, yes, you will get a whiff of that scent over in this corner of the room. So the natural tendency for the perfume molecules are actually to move and to spread spontaneously without any outside assistance. Right. So in this case, we'll just call them the scent molecules spontaneously spread out, spontaneously uh, distribute throughout the room. Okay, and that's something that you've seen, that you talked about, you know from experience. The same thing can happen if you're in a room and maybe there's some smoke being generated in one corner of the room. Well, spontaneously, those smoke particles will start to distribute throughout the room. They're not going to stay in one particular spot, right? And that's a spontaneous process in that particular direction. Now, a non-spontaneous one is one that is the opposite of that, right? So for example, a non-spontaneous process can only proceed with outside assistance. Okay, so a non-process proceeds with some sort of outside help. So in other words, if for instance, we have the situation here, what are the chances that you think that these perfume molecules or these scent molecules will spontaneously go back into the bottle? Right? What are the chances? That is not going to happen spontaneously, right? So that's a that process, if you wanted to do it, if you wanted that to happen, you will actually need to provide some sort of outside assistance. You have to go in, collect all the molecules somehow, and then stuff them back in that bottle. that is a non-spontaneous process, right? So for instance, the scent molecules going back into the bottle, right? That would be non-spontaneous. It's not going to happen without any outside assistance. So generally, what we can say then is processes that are spontaneous in one direction are then going to be non-spontaneous in the opposite direction. Yeah, and there's a good example of that occurring. Another example would be, for instance, if you have, let's say a container here, and you have a block of ice sitting in it. Okay, so if we had a temperature, let's say a room temperature or any temperature above, so 0 degrees Celsius, which is the melting point. Okay, the spontaneous process at temperatures above 0 degrees Celsius would be the ice melts. And that would be spontaneous. That happens on its own. You know this from experience. You set a block of ice out on the table or in a cup at home, it melts because the temperature is above 0 degrees. Similarly, if you have a container with some liquid water in it, so this is H2O, this is liquid. Okay, at temperatures below 0 degrees Celsius, so less than 0 degrees Celsius, the spontaneous process happening here is that the liquid water freezes. Okay, so the direction of spontaneity for a process can be affected by external conditions, right? So in this case, the temperature of the room or whatever affects which process is spontaneous and obviously which physical state we're actually starting with. So that's something that we want to keep in mind when we look at spontaneous versus non-spontaneous. So generally, what we're going to say is if we know one process is spontaneous in one particular direction, the opposite process is going to be non-spontaneous under the same conditions.